Now, in the last video, I covered how to use trigonometric identities to make the integrand of an integral easier to evaluate. And we talked about situations in which we substitute trigonometric functions of trigonometric functions. And then we also looked at three situations where we have a square root of a function involving a square root of a squared and x squared. I wanted to give an example of the latter case. So here our example here. Let's try to evaluate the square root of 16x squared minus 9 over x dx. So you'll notice that we could reformulate the function under the radical in terms of x squared and a squared. And so let's do that. Let's factor out a 4 from this. So we get the integral of x squared minus 9/16 all over x dx. And this involves the function square root of x squared minus a squared, where a is equal to 3 over 4ths, because when we square a we get 9 over 9/16. So the integral has the form of the square root of x squared minus a squared over x dx. Of course, we have a 4 out there, but we can always deal with that later. So let's just use a as our general number that we're subtracting from x squared. And if so, we can say that x is equal to a secant theta, and therefore dx d theta is equal to secant theta tan theta. And I just looked that up in a table since I couldn't remember it. So, right, the derivative of secant is secant times tangent. And therefore, the square root of x squared minus a squared is equal to a times the square root of secant squared minus 1, and that's equal to a tangent theta, as I presented in the last video. So when we substitute these functions of theta into our integral, we get a tan theta in place of our square root right there, and then for dx we have secant theta tan theta d theta all over a secant theta. And so we have so the a secant thetas cancel out, and so what we're left with is the integral of tan squared theta d theta. And we can do a trig substitution there. When I'm realizing I forgot to, when we take the derivative of x, we need another a in front of there. And so we need an a right here. And this gives us an a in front of the whole integral. And so, right, so we can do a trig substitution for tan squared theta, and that's equal to secant squared theta minus 1 d theta, because we can look up what the integral of secant squared theta is, and this gives a times tan theta minus theta plus c. Because the integral of secant theta squared theta is tan theta, and when we integrate 1, we get theta. So now we have our solution in terms of theta. Now we have to express our solution back in terms of x. So let's look at how x and theta relate. Let's draw a right triangle, the angle being theta. And x is equal to a secant theta, which is equal to a over cosine theta. So that means that if the width of the bottom dimension of our triangle is a, then x is the long dimension of our triangle, because x times cosine theta will give a. And then the vertical dimension of our triangle is just the square root of the radial arm, x squared, divided by this bottom length of our right triangle. So that's a squared. So a squared plus this squared is equal to x squared. So this means, if we look at the geometry, that tan theta is equal to the square root of x squared minus a squared all over a. It's right, so it's the opposite over the adjacent, being tangent theta. And this gives us a times the square root of x squared minus a squared over a minus the inverse tangent of square root of x squared minus a squared over a plus c. And so this gives our solution to this integral, but the original integral was an integral of this form multiplied by 4, and with a is equal to 3/4. So our solution is 4 times 3/4, which is just 3. So we have 4 times 3/4, so that's 3 times the square root of x squared minus 9/16 all over 3/4 minus the arctangent of the square root of x squared minus 9/16 all over 3/4 plus c. And this is our solution. Okay, so that's our example, and I will end this video here.